All right. So last time we talked about Rice's theorem, which proves that every non-trivial property of decidable or recognizable languages is undecidable. In other words, not only the halting problem is undecidable, there's no algorithm for it, but an infinity of other problems are undecidable too. Properties of recursive languages, languages of Turing machines. In other words, it's very hard to tell what a Turing machine does or doesn't do, not just halt, but almost any other property of the language of the machine is undecidable. We gave lots of examples. It's a very pessimistic result. And we showed where the recursive, recognizable languages are. Recursive is another way for this, another word for decidable. It doesn't mean recursion like calling itself, but it's a historical word meaning decidable or recognizable. And so that's sort of the landscape so far, right? We have the regular languages, the context-free languages. Context-sensitive we haven't talked much about, but we'll say some things about it a little bit. And then, of course, the decidable languages, those that can be decided by some algorithm, no matter how inefficient. And then things that can all be recognized but not decided. You can tell the yeses, but not necessarily the nos. And that's usually done by simulation. And of course, there's lots and lots of things beyond that are not recognizable and not even finitely describable. There's the halting problem. There's the complement of the halting problem. They're right there. And we'll skip a little bit about context-sensitive grammars. I want to hit another issue that I think is more pressing. Now that we've seen that almost nothing is decidable in some sense as far as properties of recognizable languages, I want to introduce computational universality. In other words, go in the opposite direction and say what we can do, because we can still compute a lot of things, even though we cannot compute a lot of things too. The infinitude of things that we can compute is uncountable. The things that we can compute is countable, much smaller, but still both are infinite. So we'll talk about the Church-Turing thesis today, and that's in chapter 3 of the book. And computational universality, a very interesting topic. We don't have to compute using silicon, obviously. There's lots of ways to compute. You can compute using an abacus, or using your fingers, or using lots of other things. Biological computers, we are examples of such. So there's many other systems. We already saw how to compute things using grammars, what the grammar accepts or doesn't accept. It's a way of computing or deciding a language. And Church himself, Alonzo Church, invented lambda calculus, which Turing showed was equivalent to Turing machines, but that's another symbolic way of computing. And there's several other things. We won't harp too much on those, but post-tag systems, mu recursive functions. Cellular automata you've probably seen, like the game of life, Conway's game of life. It turns out it's universal. You can construct arbitrary computers using the game of life by setting up adders and registers and ALUs and memories. It'll be a very big construction, but it'll compute arbitrary things. So you can actually construct a game of life configuration that'll play chess with you, grandmaster level chess, or any other algorithm embedded in a plane of cellular automata. And remember, cellular automata is something that was invented by von Neumann, of which Conway's game of life is a special case. So that's another way of computing. It's not particularly convenient to program cellular automata. You have to construct very large configurations and debug them and make sure they work and do exactly what you want. But you can, is the point. And of course, we already know Boolean circuits are enough to compute almost, anything that you can think of as computable, right? And our silicon computers, our iPhones, our cell phones, our computers, our laptops, our tablets, they're made of essentially Boolean circuits. And from that, you can, from a few simple Boolean circuits and not, you can construct any functionality that you want. And of course, we already saw that you can compute using polynomials. Matiashevit's solution to Hilbert's 10th problem settled that one. And you can compute using DNA. Every time you look in the mirror, you're looking at a DNA-based computer, a chemical computer, protein computer. Right? In fact, that computer is so good that it invented all these other computers and computation systems. We invented this stuff. They didn't invent us, right? We created all these other machines, not the other way around. But computationally, they're equivalent. You can compute using billiards. I'll say a little bit about that because that's surprising. How can a game of billiards compute arbitrary functions? We'll get to that in a second. And of course, we know that Turing machines can compute too. We've been saying that for weeks. And there's been a long perennial question about what's the smallest Turing machine that can actually compute anything you'd like. The smallest universal Turing machine, i.e. compiler. And for a while, we knew about machines with seven states and 4 characters in the alphabet, or 2 states and 5 characters in the alphabet. But there's a trade-off between the number of states and the characters in the alphabet. And for a while, we didn't know if a machine with 2 states and 3 characters actually exists. And Stephen Wolfram, the founder of Mathematica, put a huge bounty, like a $25,000 reward, on anybody who can find a 2-3 machine, a machine with 2 states and 3 symbols, Turing machine, 2 states and 3 symbols, that can do arbitrary universal computation. And for a while, nobody knew whether it's doable, or actually for decades, nobody knew what the answer is. And then some undergraduate, within a few months of the prize money, won the prize. And he found a machine, and there it is, 2 states and 3-character alphabet. And that machine is a universal Turing machine. Based on what you feed it, it'll compute arbitrary functions. If you want prime numbers out of this thing, you have to give it a specific string that will be the source code for a prime number program encoded for this Turing machine, and so on and so on. You want this machine to play World of Warcraft? It can. You just give it the right initial string. And don't get me wrong, it'll be a very long, complicated initial string. But at that point, it'll do arbitrary computations based on that string. That's what it means to have a universal Turing machine. A machine can simulate any other machine based on the input that you give it, like a compiler does. A compiler is a universal Turing machine. It's a polymorphic program that, based on what you give it, it can do arbitrary computations. You want to do prime numbers? You give it a certain string. That's a prime number program in Java. It'll compile it and run it. Now you got prime numbers. Same compiler could do something else if you give it a different input string, namely a different program. That's a compiler. Any questions about what this does and what it is? And look how small it is. That's the whole thing. Right there. That's how ubiquitous the notion of computational universality is. It doesn't take much to get arbitrarily complex. So the question of whether this particular machine holds on any given string, undecidable, even though it has 2 states. Because it's universal. It can do whatever other machines can do based on what you give it. So you can construct universal computers out of Lego, out of Tinker Toys, out of Meccano, out of vector sets. Lots and lots of ways to construct universal computers that can do arbitrarily complex functions or functionality. Here's a computer that plays tic-tac-toe made of Tinker Toys. Just wood blocks and wood strings, and it works. It plays perfect tic-tac-toe, even though it's made of wood and string. Here's a way to construct computers out of nuts and bolts. So this thing here is a NOT gate, because there's a spring here, and if you press this piston presses in on this lever, this goes backwards. So the input is the opposite of the output. You press it in, the output retracts. You pull it out, the output extends. This one is an OR gate. Either one of these levers or plungers get pushed, and as long as one of them gets pushed, this whole thing gets pushed. So the output of this mechanical nut and bolt kind of little device is the OR of the 2 inputs. How many get this? Straightforward. This one is an AND gate, and that's simply using De Morgan's law on the first 2. How many get that? So what you'd expect. And that works exactly like an AND gate should. And you can also, so once you have these 3 gates out of nuts and bolts, you can construct them like Boolean circuit elements to construct arbitrary things, including playing chess or any other complicated program that you want, simply from nuts and bolts. How many get that? Just pile on enough of them to simulate arbitrary logic circuit. Right? But it was kind of a surprise to us that you can build arbitrary machines out of nuts and bolts, or Tinker Toys, or water pipes. Here's how you can build a machine out of water pipes. This thing here is a transistor. Basically, it's a valve here, and if this valve is pushed, water can flow this way, and it's a one-way flow because there's a little one-way flow, backflow preventer there that won't allow it to flow the other way. So it's a one-way flow with a valve. That's what a transistor is. This thing here is another way to do just a one-way flow period without a valve. That's basically a diode. Right? So between those elements and a couple other elements, you can build arbitrary complex circuits out of water pipes. And that's kind of amazing. Right? There's a blueberry muffin universal computer. It's a joke, but here's the thing about billiards. Remember I mentioned that a couple of minutes ago. It turns out that you can compute arbitrary things using the game of pool. So here is a gate made of billiard balls. So if two balls come into here, they'll collide. If they come in at the same time, they'll collide, and they'll take these zigzagging paths. And a ball will come in here only if there's nothing here interfering with it. But a ball will come out this way, in this trajectory, only if there's one here and here simultaneously, and so on. So you can build logic gates out of billiards. Here's another configuration. This one requires a little bit more infrastructure around like a box. But if two balls come into here and here at the same time, they'll collide right there. We're assuming, inelastic collisions and no friction and all that good physics assumptions. That's fine. This is all, a construct. And they'll collide here, and one will go here and here. They'll collide against these walls, collide again here, and go out this way and this way. And this will be the AND output of this thing. So only if two balls come in at the exact same time will one ball leaves out of this one. Otherwise, they won't. So it's an AND gate. And Richard Feynman, the great physicist, came up with that construction. Once you can construct these simple gates out of billiard balls, again, compound them in arbitrary complex combinations to construct arbitrary functionality. So a billiard ball configuration, if you set it up just right, with enough billiard balls on the table, can play chess with you, or any other game, or any other functionality whatsoever, which is kind of amazing. Who would have suspected that? That also gives you kind of a hint as to why billiard is such an interesting game and hard to predict the outcomes and so on. And I guess we get one more reason. It's universally complete. Right? You can simulate an arbitrary Turing machine using nothing but a very large billiards table and lots of billiards balls. Don't get me wrong, it won't happen on a small one with only 12 or 15 balls. But if you have thousands of balls and a very large table and no friction, of course, and so on, and control over initial conditions, with high precision, yeah, you can get a billiards game to do arbitrarily complex things. So if I show you an arbitrary billiard configuration, I say if I hit the white ball here, will the red ball end up in the left upper corner pocket? That question is what, technically, algorithmically speaking? If I ask you where a particular ball will end up in some pocket or not, how hard it is to answer that question. What's your algorithm for doing that? See if you understand what I just told you. Yeah, and so in a shorter answer, what's the algorithm? So that's a condition, and it's true. But if I ask for the algorithm, what would you tell me? Take a wild guess. There is no algorithm. It's equivalent to the halting problem. How many get that? It's a universal machine that these balls are simulating. And we don't know how to answer questions about universal machines. In fact, we know something even better, that there's no way to answer questions about universal machines, arbitrary computations, whether they halt or don't halt, or any other question for that matter. Halting is the simplest question you can ask about an algorithm. Right? Everything else is even worse. So whether a ball, when hit in an arbitrary billiards configuration, will end up in a corner pocket, undecidable. Literally, technically, and mathematically provably so. Any questions so far? Which is fascinating. Who would have thought that billiards could be that hard? I mean, we know it's not easy to master it. But that's not saying anything mathematical. They're right there. And now we know it's not just not easy to master. We know it's impossible to master, even for an omniscient entity, using any algorithm whatsoever. That's how hard it is. Amazing. So billiards is equivalent to universal Turing machines, to arbitrarily complex computations. Next time you play pool with your friends, you might want to mention that. Of course, it may kick you out of the room, but still, you'll be right. So here's another interesting, cool thing. So gravitational systems, right? So we used to think, we understood gravity really well. And I'm talking about Newtonian mechanics. I'm not even talking about quantum gravity or quantum mechanics or anything esoteric, just inverse square law of Newton. 400-year-old discovery, still in effect today. That's how we send people to the moon and things like that. So elliptical orbits are implicit in the inverse square law. Kepler found that out, right? And if you have multiple bodies revolving, you have elliptical. These are elliptical orbits around a central body, whether it's planets around the sun, whether it's moons around a planet, right? Jupiter and Saturn have dozens of moons, but they all have elliptical orbits. But things can go really funky in gravitational systems. Here's an actual gravitationally correct simulation. So you have a pair rotating around each other coming in from here. That's the blue and the green. A third one comes in, interlocks with them gravitationally, matches up against the green, and the red one gets ejected. That can actually happen. How many get this example? All right, and we knew about examples like that too. This is also implicit in the inverse square law, except not as simple as an elliptical orbit. This is more complex. But here's the kicker. Things get even more complex than that. Here's a stable gravitational system involving three bodies, and they're doing the figure 8. This can actually happen. We haven't found one in our own solar system yet, but this completely respects the inverse square law. Moreover, this is stable. Stable means you can take small perturbations, like push one of those a little bit, and it won't make the whole thing collapse and disengage. They'll keep going in a figure 8. Or you can change the masses slightly by epsilon, and it'll still keep going the same way as it did with this figure 8, slightly perturbed. But it's a stable orbit among three bodies, all doing the figure 8. We had no idea this thing is possible up until a few years ago. We didn't realize this is a solution to the inverse square law of Newton. We just thought ellipses and maybe a few esoteric things, but not stable, continuous figure 8 orbits. How many new figure 8 orbits could actually happen? Okay, I see no hands coming up. It's not obvious. And it wasn't obvious to all of humanity for 3.5 centuries since Newton's time. So I'm just showing you how complicated things can get if you just have a quadratic polynomial with a square in the denominator, inverse square. We already know that polynomials can do arbitrarily funky, complicated things, from Matiashevit's solution to Hilbert's 10th problem. Polynomials are computationally universal. But here's a very dramatic example of just three bodies following the simple inverse square polynomial, and it's actual gravity in this real universe. It's nothing esoteric that doesn't exist. So it's like 3D billiards, basically. And I'll show you a few more strange orbits, again, that we didn't know existed until a few years ago, as solutions to Newton's equation. Right? And there's poor Kepler trying to explain to his colleagues, he says, so you see the orbit of a planet is elliptical, and he's taking for granted what they don't know, right? First guy thinks, what's an orbit? Says, what's a planet? The third guy says, what's elliptical? So you have to define your terms and make sure there's enough infrastructure to then take the next leap forward, intellectually speaking. And we've been doing this in this course all along. Right? First we got comfortable with infinities and one-to-one bijections and on and on and on. And finally, we proved undecidability and a great many other things. So here's that figure 8 three-body orbit. And this could be extended to arbitrary number of bodies. Again, in a gravitationally correct inverse square law, pure Newtonian physics, nothing esoteric here. And this is also stable. Stable, again, means any small perturbation of this with respect to positions, mass, or velocities continues this configuration. It doesn't just fall apart at the slightest provocation. Here's another one, figure 8, but this one is not in the plane like this one. This one has a 3D skew to it. So this is still a figure 8, but it's not planar. Again, very different than the first one, and even more surprising. You'd think if it was a figure 8, it would have to be all flat in the plane. No, it could be curved in space and still respect Newton's inverse square law. Here's another one. Each one takes a completely different path than the other. So they're not engaged in some figure 8. Each one takes its own path, and it's stable Newtonian orbit. And here's yet another one for three bodies. So you're beginning to see, this innocent-looking equation of inverse square, right, where the square here is in the denominator and the rest is just constants, masses multiplied together times some constant, gravitational constant, can give you very strange esoteric behavior. And that was just unexpected, surprising, shocking even to physicists. 3.5 centuries after Newton wrote that law down, and we all thought we understood it completely. Right? Here's a few more. Here's 4 bodies doing this non-planar, each one following their own path, stable orbit. Here's 6 bodies, 3 doing one orbit, 3 doing another, completely gravitationally stable. Here's another 6 that's different. This is 2, 2, and 2. So now you're beginning to see the diversity of different strange orbits that are possible. And we had no idea for all these centuries, even after we knew this equation. These all arise from this equation right here. Now, that's not to say that you'll find these all over the universe, right? It'll have to be pretty unlikely set of coincidences for this to actually be found in real space somewhere. But the point is, it's possible. You know, just like it's unlikely that you take a pool shot on a billiards table and all the balls will fall into all the pockets instantly from one shot. That's unlikely, but the point is it's possible. In fact, some pool showmen, grandmasters in pool, do exactly that as an exhibition. They sink all, 10 or 12 or 15 balls all at the same time, carefully orchestrated initial layout, right? So gravitational systems are computationally universal. Question? Let's just call it epsilon. Of course, there's a limit to that, because if you take one and put it over there, all bets are off. Things will begin to drift. But if you slightly perturb any one of them by, 1% or some small amount, whether it's momentum or add mass or subtract mass, it'll slightly be perturbed, but still remain stable in a similar looking configuration. I'm not saying it won't change at all. It will change slightly, but it won't fall apart, is the point. So that's an extra added feature of these. They're not like tethering on the edge, like something that's in equilibrium, but only slightly, and if you blow on it, it'll fall apart, like a card standing on edge or some pencil standing on edge. No, it's more like this, actually, where you can perturb it and it'll stay there. Of course, if you perturb it a lot, something bad will happen. But that's what I mean by stable. Good question. Any other questions? So you can compute using planets. I'm not saying it's an efficient way to compute. Planets move pretty slowly through the universe, and it takes 100 million years for our solar system to go around the Milky Way, and on and on and on. But the point is, it's possible to compute using gravity systems. That's how ubiquitous and common computational universality is. So this whole lecture is saying it's everywhere. It's under our noses. It's us, protein computers. It's Turing machines. It's the game of life. It's billiards. It's gravity. It's the whole universe computing everywhere all the time in all sorts of ways. And that's one of the reasons it's hard to predict what happens in the universe, whether it's gravitational systems or collisions among particles or some simulation of physics or chemistry. Those are notoriously difficult. Now you know one more reason why they're hard. It's not just about complicated program to get all the right codes and the right interactions and simulate inelastic collisions and particle interactions and all. That's hard enough. But even if you do all that correctly to extreme accuracy, you still have undecidability rearing its ugly head at every turn. And that is not a hurdle that you can surmount, because we know there's no algorithm for undecidable things, and they're everywhere. So this brings us to the Church-Turing thesis. And it's not just a Church-Turing thesis. There was a whole bunch of these people in Princeton and the Institute for Advanced Study in the 30s, including Turing and Einstein and Gödel. There's Einstein and Gödel walking to their office every morning from their house across the lawn to the Institute for Advanced Study. And when Einstein was asked once, what's your favorite thing about working at the Institute for Advanced Study, he said, my morning walks with my buddy Gödel. And there they are. And anybody recognize this guy in the middle here? This is Johnny van Neumann on the right. This is Ulam, Stanislaw Ulam. Johnny van Neumann and Ulam invented the nuclear weapon, the fusion bomb. Not the fission bomb, that's just a spark plug for the fusion bomb. But anyway, this guy here, young Richard Feynman in his early 20s. This is in Los Alamos, the Manhattan Project. So a lot of these guys were kind of sharing ideas and thinking about these things, universally computable things and computational universality. And of course, Turing invented these famous Turing machines, and Gödel's incompleteness theorem, and the things are related, and Alonzo Church was there too. So, really it should have been called the Church, Turing, Gödel, Einstein, von Neumann, Ulam, Oppenheimer, Feynman thesis. But, we just call it the Church, Turing thesis, and sometimes just Church's thesis even. But it's really the brainchild of all of these people, among many other things, not the least of which was the Manhattan Project. So what does it mean to be computable? So the Church-Turing thesis says whatever is computable using Turing machines. But what does it mean to be computable? You can think, you can ponder, you can compute, you can analyze, you can problem solve. You know it when you do it because, we're human and that's what we do. And a human can think and ponder and problem solve and compute with or without prosthesis. So here's a brain prosthesis. It's an abacus. It's not a very sophisticated one, but it helps you speed up your mental computations. How many have ever used an abacus or seen an abacus? All right, it's been used for many, thousands of years, really. Nowadays, we have better prosthesis for our brain. They're called computers. Some of them are even more impressive than that. They're called supercomputers. And here's a Cray 1 supercomputer from the 70s. This one cost $10 million and weighed 2 metric tons. Of course, today your iPhone is faster and more powerful than it, and it's in your pocket. But still, nobody would say that with these computers and brain prosthesis, you can do anything that you couldn't do without them. Of course, you can do it faster, but you couldn't do it better. How many get that? Because you can do whatever a computer can do very, very slowly. If you had 1 billion years, you can do whatever your iPhone does in 1 minute. You can take 1 billion years and do yourself. One little tiny instruction at a time, simulate the machine code. It's not going to be a fun billion years, don't get me wrong. It'll be very boring for you. But the point is, nothing will stop you from doing that, or us as a species from doing that, if that's what we wanted to do. So these prostheses just add speed. They don't add capabilities. They're not a superpower. They just allow you to do things faster, but not allow you to do more things that you couldn't do without them. Okay? So when we say to compute or to think or to problem solve, we mean you and whatever prosthesis you want to throw in that just adds speed to your capability, like computers and abacuses and calculators and beaded strings or whatever it is you want to do or scratch paper, whatever it is you want to use. Okay. On the other side is a Turing machine. And we already talked about that and what it can do. The Church-Turing thesis says they're equivalent. In other words, there's nothing that a Turing machine can do that a human cannot, given enough time. But the interesting thing is the opposite. The opposite says that there's nothing a human can do a Turing machine can't do, given enough time and the proper programming. That is not so obvious, that part. Because it's obvious that you can do what a Turing machine can do, because you can simulate it by hand with a paper and pencil and to trillions of steps. It'll be long, it'll be boring, it'll be tedious, but you can obviously do it one step at a time. But that a Turing machine can do everything that you and I can do, that's more challenging to believe. That's more incredulous. That's less obvious, right? That computers can really do everything we can do. We're already seeing a lot of signs of that as time goes on, right? So the Turing thesis says anything that's intuitively computable to a human is also computable by a Turing machine or an algorithm. And we'll go deeper into that in the next few minutes. But also right now it should strike you that it's not just Turing machines that are on this side. It's all these other equivalent systems, right? Mu systems, lambda calculus, Boolean circuits, biological computers, the game of life. These are all bunched together because they can all simulate each other pretty easily. And we already know that billiards now is arbitrarily computationally universal, and now gravitational systems can do arbitrary computations. Water pipes can do arbitrary computations, and so on and so on. So really on this side of the equation, or the equivalence, is all of these systems bunched together. That's the easy part, because we already know how they can all simulate each other, right? You can easily simulate Boolean circuits, using a Turing machine. You can also simulate the game of life using Boolean circuits. So you can simulate polynomials using billiards and so on. And you may have to compose some of these simulations and to get to the right end-to-end kind of simulation, but that's okay. How many get that? That they're all equivalent to each other. Okay, good. That's a lot of hands. Nice. So why is it called a thesis and not a theorem? Why not just call it the Church-Turing theorem? What do you say to that? Why kind of tippy-toe around this issue and call it a thesis rather than just a mathematical theorem? Like all the other theorems we've been proving the whole while this entire semester. Why do you think that is? We wish we could call it a theorem, but we can't. Not yet. Why? Hasn't been proven. And what's the problem of proving? Why not just prove it then? She's right. It hasn't been proven. Not yet. And maybe not ever even. It depends which way technology goes in the next few centuries or even decades. Yeah. Yeah, you'd have to somehow show how one of these computational systems, and we know they're all equivalents. If you can do it in one, you can do it in any of the others because they all simulate each other. But say a Turing machine or a program can act like a human brain, exactly like a human brain. And what's the problem with that? Why can't we just write a complicated enough AI program and call it, high fidelity human brain simulation? Yeah, that's one of the issues. And another issue is we don't exactly know what the human brain can or cannot do. We know certain things it can do, right? We can build, this building where we're all sitting. We can build, these other devices that we all use every day. We can build planes that fly and spaceships that go to the planets, and can, build televisions that show movies and all that. But that's not the complete capability of the brain. That's just a few things we've done so far, and we keep doing new and exciting things, and they happen every day, inventions and discoveries, and we put them together, and we engineer our way out of all sorts of issues, and we engineer our way into all sorts of problems too, but that's a different matter altogether. But it's hard to circumscribe all the stuff that the brain can or cannot do. We have a lot of anecdotal examples, all these things I mentioned. It's hard to completely characterize a complete set of what the brain can and cannot do, a human brain. And we keep surprising ourselves every single day, for better or worse, right? We created the web, but we also created nuclear weapons. I mean, they're both technologically amazing, but morally, one is not like the other. So it's hard to describe what a brain can do, and therefore that's one of the reasons we cannot prove what a brain can or cannot do, or compare it to some other system's capabilities, because it's hard to circumscribe it and exactly define it and delineate exactly what a human can or cannot do. It's kind of intuitive. Also, we're not good about thinking about ourselves, introspecting about our own brain. Right? How many tried writing a program that writes itself out, that prints itself out? So you know what I mean. It's hard to do. That program was very short. But you spend a lot of time trying to figure out how to make it work. Right? It's hard for a program to introspect, to write out its own source code. Right? And that's another subtle reason why it's hard for us to completely circumscribe our own capabilities, because we'll need our brain to think about our own brain and every last little detail and aspect of it, using the brain that we're trying to wonder about its capabilities. So it's like a recursive exercise. It's like a program trying to print itself out. For similar reasons, it's also kind of dicey. Not impossible, but tricky. So we know what an abacus is, what a supercomputer is. Those we can define. We know what all these systems are. Those are completely well defined. They have mathematical descriptions. We can prove lots of theorems about their equivalences. We've been doing that all along this semester. But the one thing in this slide, that's not completely defined, it doesn't have an inverse square law or some fluid dynamics equations or some chemistry set of propagation rules and mathematical number theoretic description. The only thing that is hard to figure out here is this thing here. And that's why it's called a thesis and not a theorem. Okay? just so you know. And it will probably stay that way for a long, long time to come. And some people even muddy the water additionally to all these technical reasons. And they say, well, a human has a soul and a computer doesn't. That's why they'll never be the same. Well, that's not a very scientific argument. That's not a very mathematically precise argument. It's not even well defined, what I just said. What is a soul? You know, quote unquote, define that. Well, it's hard to do. But some people live and die by these beliefs. That's okay. But I'm just showing you another dimension of complexity around this issue. You know, that kind of borders on religious beliefs and philosophical issues and other things. Aside from all the mathematical and technical issues, there's other issues yet piled on really deep and high on this. Some people just don't want to believe that a computer can ever replace them. They feel it's an insult to their humanity. I'm not one of those people. I think if computers can do exactly what I do and more, I'll take a bow, first thing. You know. Now, you know, it may also go sideways, right? Like in the movie Terminator, when machines got too sophisticated, you saw what happens, you know, I'll be back, and all that, you know, some bad news, right? So it's not, but we're not talking about whether it's good or bad. We're talking about whether it's possible for machines to do what we do, and maybe even more. Why stop there? Right? So there's lots and lots of issues here, including very fuzzy definitions and people's psychological resistance to ever equate themselves with a machine and that kind of thing. And of course, the technical stuff that we talked about. All right, so that's why it's called a thesis and not a theorem, but that's what it is. So what can computers do? We already saw what they can't do. Rice's theorem is a lot of infinite, uncountable number of things that computers can't do. But things that they can do, obviously, is play tic-tac-toe and solve puzzles and Towers of Hanoi and Sudoku and all sorts of things. You can probably imagine how you implement code to solve all of these, you know, puzzles and games and so on. And people have, and works pretty good. Computers can do it, and they can do it well. They can solve Rubik's Cubes, and they can solve even more complicated puzzles, right? I actually have some of these puzzles. Actually, I have all of these puzzles. Some of them have hundreds of pieces. Did I ever bring into class? No, I haven't. Okay, remind me to do it. I'll do it before too long. Just show and tell. But I have a Rubik's Cube that's 11 by 11 by 11. I mean, you know, the thing is like this big. It costs, I don't know, $300, and it's very, very hard to solve. Anyway, computers can do all that pretty straightforwardly, if nothing else than by brute force. And of course, there's much more efficient algorithms than brute force. And they can play games like tic-tac-toe and checkers and chess and the game of Go, right? And we already have computers beating humans back in '97, right? Deep Blue versus Kasparov. Kasparov wasn't too happy about that, but ever since then, computers were the world champion in chess, and now they so outstrip humans in terms of chess capability, it's not even close. The best chess humans can play on the ELO scale of chess rating at, say, 2,800, 2,850, and that we're talking Bobby Fischer and Kasparov. Who's a current chess champion? It's a young guy from Norway, Norwegian guy. Magnus Carlsen. He can play at almost 2,900. It's one of the best players ever. Computers can play at 3,350. No human has ever exceeded 3,000. So, and your iPhone can play grandmaster chess with you that no human can beat. And that's how chess has been kind of completely algorithmically plowed back and forth and well solved. Go, not so much, although Google AlphaGo won the World Championship Go just last year. For the first time in history, a computer beat a world champion in Go, and of course, it'll only get better from there. So Go just been conquered recently. Chess has been conquered 20 years ago. Tic-tac-toe has been conquered, you know, centuries ago. You know, it's a very simple algorithm. The tree size is very small. Not a whole lot going on in tic-tac-toe. That's why it's not that interesting. But for chess, the game board, the game tree, all possibilities, as represented as a tree, move, counter, move, counter, counter, move. 10 to the 50 different nodes in that tree. Each node is a board position. Go, 10 to the 171. That's bigger than a Google. That's one of the reasons Go hasn't been solved until very recently. Or actually, it hasn't been solved, period. It's just been improving and improving, finally past human capabilities of playing, but still not really solved completely. Checkers has been solved completely, actually. It took a while because it's 10 to the 20 different possible game boards. But just recently, about 10 years ago or so, checkers have been solved completely. Turns out it's a draw. So checkers tournaments are now not that interesting because they know that the first player will always win, and you can sort of learn the best strategy to play. And so now, how do they play checkers tournaments, do you think? Now they know that checkers is technically a draw for the first player. Or I mean, actually, it's probably a win for the first player. So how would you still conduct a tournament if you know the complete winning strategy for checkers? What do you think? If you're running a checkers tournament, how would you still make it interesting for the audience? Yeah. Speak it? Okay, or we can play blindfold and make it extra. Oh, speed. Okay, speed. Yeah, you can play speed checkers, allow only a few seconds per move or something. What else can you do? That'll work. What if you don't want to force them to play that fast? You want them to actually think deep. Yeah, you can change things. Or you can make the first few moves random, right? Have a random number generation. It'll make the first 3 moves, 3, 4, 5 moves, and then let them play. Of course, you have to make them play a bunch of different games. And if they can adapt to the initial first random moves and still recover well against their adversary, and you play a bunch of games to kind of even out kind of the randomness thread, then you pretty much, after a while, know who's the better player, right? So this just happens, yeah, recently. And some games have chance, they have dice, they have randomness. We're not talking about those games, but you could. That can. And there is, of course, Kasparov not having a good day back in '97 or so, losing to Deep Blue. He was sure he was going to win, and there was a big prize money involved, so was trying really hard to win. There's even a movie made about it, very dramatically called, Game Over, Kasparov and the Machine. No feelings, no fear, no contest. Reality may differ slightly, but still, it was, the brain's last stand, on the cover of Newsweek. Of course, nothing terrible happened anytime real soon. Machines still haven't taken over. We don't have Terminators chasing us down yet. And this was 20 years ago. But it was pretty amazing, an amazing day. More recently, this was just 5, 6 years ago, IBM Watson beat the world champions at Jeopardy. That's harder to do than chess because it involves speech and natural language understanding and parsing of grammar and large repository of trivia information and a big database and on and on and on. But still, look at the difference between the scores here. I mean, it wasn't even close. So now computers have beaten us in Jeopardy too. And there's still games where humans are still better than machines, but fewer and fewer with every passing decade, every passing year, actually. And there's the AlphaGo in 2016, just a year ago, beating the world champion. Right? Lee Sedol, there was $1 million purse, so he had a huge incentive to win, not to mention his reputation. There's the actual game, one of the games, showing as a video. And he lost. I think he won 1 out of 5 games, technically. And he lost the other 4. And even that was touch and go, that one game that he won. So probably next year, no human will ever beat a machine again, the top machines, top algorithms, I should say, in Go, same as chess. So the transition just happened. And, other things we can compute, and this is right around the corner, literally, corners, autopilots, algorithms that allow you to drive cars by themselves. So the Tesla Model S can go autonomously. It's already been doing it for 2 years on the freeway, and it's about to go autonomous in the streets, in city streets, which is a tougher algorithm because lots and lots of special cases. Little kids, pets, balls flying around, there's trees and lots of cross traffic and stop signs. Freeway driving, without all these issues is a much simpler algorithm, much smaller case statement of branching around. So on top of being autonomous, it goes 0 to 60 in 2.3 seconds. Actually, this slide is old. I keep having to change this number down. It's now 2.3 seconds, 0 to 60. So you can beat Ferraris, Lamborghinis, and Bugattis in a drag race. Amazing for an electric car, actually for any car, especially since it's a 4-door sedan and these other cars. They're 2-door coupes, and They don't have any trunk space, and you can't take them to the supermarket. And this is a family car. So the family car can actually outrace Ferraris and Bugattis. These are $1 million, $2 million cars. That's amazing. So that's an extra bonus besides the fact that it's a really, really smart car. It can actually drive itself autonomously, and you can very soon summon it from your iPhone app. You can say, come pick me up, and the car by itself, empty, will come pick you up from wherever you are, or drop you off and then go park itself somewhere, and you don't have to worry about it. Or while you're working or sleeping, the car can Uber itself around town, make money for its own down payments, and your car will then be free. Actually, it can be an income stream. Whether you want to do it or not, it's optional, but it's an interesting option to have, is to have your car go and carry its own weight financially. That's a year or two away from now. It's not one day, far future, sci-fi kind of scenario. This car has already been driving itself on a freeway 2 years ago. So this is already happening. So very complicated algorithm, but it started in 2005 with the ARPA Urban Challenge. People have been trying to build self-driving cars for decades, ever since cars existed, obviously. And lots of accidents, 1 million people a year die from car accidents. Most of it's unnecessary, of course. So very tough problem, but they've been trying to solve it for decades. And then ARPA put $1 million prize on this. And a bunch of college teams, university teams, a few industry teams came in and tried to win this challenge. You had to go about 100 miles through desert roads, including turns and so on, complete a course. And nobody won. So they doubled the money to $2 million, and in 2006 or 2007, I guess, 2006 it probably was, they said, okay, let's try again, this time $2 million, and then 3 or 4 or 5 of the teams won, actually. They completed the course in average speed of 30, 40 miles an hour. That was pretty good for desert driving without obstacles. Fast forward 10 years, and now we got the Tesla. So things are moving very, very fast in this technology. Look how it looked back then. This is one of the prototypes that won. Kind of a clunky old thing with lots of sensors and LiDARs and radars and acoustics and cameras, and it was all kludgy. And now, of course, it's all integrated into the chassis. You can't even see the sensors. They're all there, of course. So things we can compute keep improving, keep increasing. That set becomes more and more sophisticated. And here's a cartoon from a few years ago. It's a human representing the human race trying to desperately clutch onto things that only humans can do and computers can't do, and thereby preserve our human advantage and pride. And all these things get crossing off. So it says, only humans can understand continuous speech. And of course, that was crossed off some decade ago, when now we have Siri that can listen to you and give you answers back. It's not perfect, but it's pretty impressive. So you have to cross that one off. And only humans can recognize faces. That was true 20 years ago. Now you have facial recognition software that governments deploy on street corners with traffic cams, and works pretty good. Again, not perfect, but it's getting better and better. And so there's a few things here still left on the wall that only humans can do. Only a human can play baseball. Only a human can review a movie. So this guy is desperately trying to preserve these things, and all these things humans can do better than humans. Computers can do better than humans already. And this cartoon is only a few years old. And look at one of the things that is still on the wall here when the cartoon was constructed. Only humans can drive cars, it says. That shows you how old this cartoon is, namely just a few years ago. It's not ancient history. So that one is crossed off, even though in this cartoon it's still on the wall. So that's how fast things are moving in terms of what computers can do that they couldn't do before, and some things that they can do now that we didn't even think they could ever do, right? Like beat a human at Go and things like that. So this gap between computers, machines, algorithms, and humans keeps narrowing, keeps closing at a alarming pace. I mean, alarming is the wrong word. At an impressive and surprising pace. And if this gap will ever close or invert completely, we don't know. It's an open question. Chances are it probably will, from the speed things are happening at in terms of advancements. But we still don't know what is intelligence, or what is mind, or what is consciousness and sentience, and all these words that we invented to try to differentiate ourselves from inanimate objects. And we still consider computers inanimate objects, but not for long. Soon enough, we'll have to concede, if they can outthink us and outperform us in almost anything, maybe everything that we can do, and then some, maybe they're not so inanimate after all. And we'll have to kind of rethink how we want to differentiate ourselves from them, if at all. So it's hard to tell where this is going, but it's definitely going in that direction. And in many areas, computers already far exceeded us in their capability. Don't get me wrong, I'm not rooting against humans. I'm just saying, it's not terrible if the machines we created can outdo us in every single way. If nothing else, think about that. We created them. That will never change. They didn't create us. We created them, obviously. So at least we'll have that to latch onto, even if they far outpace us. Just like your children, one day when you have children, if you see your children eclipse you in terms of their accomplishments, their earning potential, their success, you don't feel jealous or afraid. You feel pride, right? And I think, same thing should probably be true for our machines. If they outdo us, I, for one, will feel very proud, not afraid or alarmed or threatened. But, your mileage may vary. Some people will feel threatened. That's why you have movies like Terminator. It's a Frankenstein complex, right? Terminator is a modern retelling of Frankenstein, Mary Shelley's Frankenstein. How many get that? It's an old story. It's nothing new. We created something where you can't control, and it goes haywire and turns on us, and it's exactly what Frankenstein was, and it's exactly what Terminator is, or HAL 9000 in 2001, and a great many other movies with the exact same theme. Right? So we'll see. So other things we can compute easily, like digits of pi. Right? So again, juxtaposing what we can do with what we couldn't do, like Rice's theorem, just so things don't get too depressing. We can compute lots and lots of digits of pi and other formulas. There's formulas for pi, and you can compute arbitrary number of digits. It's pretty straightforward. Computers can compute billions and trillions of digits, and some formulas of pi are more interesting than others. Can you tell who wrote this formula just from the way it looks? Who invented this formula for pi for 1 over pi? There's only one guy in history that could have. Ramanujan, it has to be, you see. I mean, you can recognize his handiwork just from the formula, the way it looks. One of the books on the website is The Man Who Knew Infinity, his story, biography of Ramanujan. Remember, we talked about him. G.H. Hardy discovered him. He went to Cambridge and so on. Anyway, that's another Ramanujan identity for a constant times pi. But computers can be implemented using these formulas and lots of formulas to compute pi and digits of pi and other irrational numbers like e and the square root of 2. And here are some of the digits. Those are pretty straightforward to do. So I'm going to show you progression now from what's relatively straightforward for algorithms or computers all the way out to what's still mysterious and undoable even now. We still don't know how to do. And we'll talk about the reasons why. So prime numbers, again, the sieve of Eratosthenes. This algorithm was known to the Greeks. It's probably the oldest algorithm ever invented, over 2,000-year-old algorithm. It's hard to get older than that. And there's theorems about prime numbers. We talked about primes a lot. So you can compute primes. Pretty straightforward for algorithms to do. And you can compute various harmonics and graphics and compute eclipses. We can do that for a long time. That's basically Newtonian mechanics applied to the solar system. You can visualize things. Here's a tesseract rotating in 4 dimensions. That's a 2-dimensional depiction of its 3-dimensional shadow. Pretty straightforward to do. We can morph stuff, graphics. Right? We can do that for a long time. Here's one that's tricky. Humor. That one we haven't conquered yet. It's hard to construct an algorithm that will be funny. Think about it. How do you construct an algorithm that will make you laugh? Just by looking at its output. And not in a bad way, but, honestly make you giggle. So here's a couple of cartoons about humor, but that one is very fuzzy. It's hard to do for algorithms, for computers. But humans do it all the time. We make jokes left and right, and we make each other laugh, and, being witty and funny and humorous. But try to do that algorithmically. You'll see that's tough. It's not impossible, right? There's some algorithms that can construct limericks, but they're only very primitive. There's like a little template, and a limerick is a very, confined and restricted form of humor, and it has this kind of iambic pentameter going on and kind of a cadence to it. But even then, algorithms will have a hard time constructing good limericks, even though it's a very, very restricted form. Emotions, that's even harder. We are driven by emotions as a species, right? Love and hate and fear, and in fact, a lot of our daily existence, the meaning in our lives, is revolved around emotions. Especially good feelings, like loyalty and justice and love and caring about people and so on. Again, algorithmically very difficult to capture those things, and not necessarily impossible, right? Try to find a derivative of love. So there's little cartoonish kind of humor here. What's the square root of love? So there's humor on top of love here, embedded in it. And again, it's very hard to put an algorithmic aspect on it. Compute it, generate it, capture it, analyze it algorithmically. But then again, it's not very well defined. If you ask a bunch of people what is love, they'll probably get a dozen different answers, right? And you can't really argue with it. It's their subjective interpretation or beliefs, and it's kind of ambiguous. So that's part of the problem why it's algorithmically difficult. But even if it wasn't ambiguous, and we could all agree on a definition of love or justice or truth or loyalty or whatever the word is, these emotions that drive us humans, that define all of our daily interactions, even if it was well defined, it would still be hard to implement. And it's not nothing, these things. I mean, these emotions dictate almost everything we do, right? How we live and our goals and our aspirations, how we spend our time, and they're the backdrop of every single novel, movie, and play we've ever produced, almost, right? So it's not that because it's undefined, it's nothing or negligible. It isn't. To us, it's very, very important. And remember, we created these machines. So at some point, if they're going to act like us, they better be important to them too, and they better start acting on it also, like we do as a species. We act on these emotions not just at an interpersonal level with other people, but as groups, as countries, as a whole society, as a whole civilization. So those are on the borderline, kind of the fuzzy edge of what computers can or cannot do yet, even though most humans kind of are okay with all that, at least, when they have enough life experience to be able to handle it. And of course, many humans can't even handle it later on in life, and they get all confused, discombobulated, and irrational about things, and it's part of the reason they call it emotions, as opposed to rationality or logic or whatever. So another thing that's hard for computers to do right now, and probably forever, is to compute large complex systems like weather, right? So here's Hurricane Gustav moving over Cuba. A lot of people died just a few years ago, 2008, and very hard to predict those hurricanes and weather systems. And there's good reasons for that. Chaos, very high sensitivity to initial conditions, like the butterfly effect, right? Ever since Jurassic Park came out, chaos and butterfly effects kind of had a bad rep because the guy was throwing them around like it was nothing in the movie Jurassic Park. But how many heard of the butterfly effect or chaos? Okay, so you've seen the movie too. It's true. A butterfly can technically flap its wings halfway around the world, and we'll have a hurricane on the other side of the world, 6 months later, by cause and effect chain. But it's very, very hard to predict it because it's very sensitive to initial conditions. And if the butterfly fluttered its wing 1 micrometer off, this storm would still come around maybe, but it would completely miss Cuba and instead hit the Bahamas. That can actually happen. High sensitivity to initial conditions. So even if you know all the initial conditions, even if you knew all the particles in this storm system, all the 10 to the 50 particles that are there, all their velocities, temperatures, trajectories, and so on, in a 3D complete map down to the atomic level, even if you had all that information somewhere, and we don't, but even if we did, we still couldn't tell you if it'll go over Cuba or hit Florida instead. Because even if you have 1 micrometer of inaccuracy, the whole thing could be off. So that's what chaos does. It kind of throws off things even if you had complete data because the accuracy is almost limited by our digital systems. And even at the quantum level, there's uncertainty principle and so on at work. So it's very, very hard to make an end run around chaos. And of course, there's insufficient data. Even if there was no chaos, we have no idea how to measure all this data with enough granularity to predict the outcome of the whole system. And of course, on top of that, there's undecidability. Even if there was no chaos, and even if it was complete data, it would still be undecidable whether it goes over Cuba or directly to Florida. How many understand that? So there's several levels of difficulty. Each one is unimaginably complex and insurmountable, and they're all layered on top of each other. And that's why we may never be able to predict the actual weather. Now, that's not to say we can't predict climate. You know, I can tell you that during the summer it'll be very warm, and during the winter it'll be pretty cold. But I'm not making any complicated prediction here. I'm just saying that's what seasons are. That's not this level of prediction granularity of weather. This is just much broader phenomena of climate, very different. Okay. So other examples, tsunamis. These are just weather systems, but in water instead of air. It's all fluid dynamics anyway, right? And we had a tsunami in 2004. That's what it looked like at ground zero. When you see a wave that high coming at you at 50 miles an hour, it's going to be a pretty bad day for everybody there. And almost 250,000 people died. It released 9.5 teratons of energy. Not megatons, not gigatons, teratons. 100-foot waves. Again, very hard to predict these things. Earthquakes, tsunamis. We'd love to be able to predict them, because at the very least it'll save lots and lots of lives and property damage. Not to mention nuclear disaster like the Fukushima reactors in Japan that went haywire because of a tsunami, and we're still seeing the radioactive after effects of that a bunch of years later. Elections. Don't even get me started on that one. It's hard to predict. I made this slide a long time ago, by the way. It wasn't recent. And this graphic actually shows you the red-blue states of every single presidential election going back to the 1800s. So if you look at this enough, you'll see the entire distribution. Why isn't there red and blue states here in the year 18, Because that wasn't part of the United States yet, right? It was Louisiana Purchase back in the early to mid 1800s and so on. Anyway, gravitational systems like billiards and planets and stars, again, hard to compute. Here's two galaxies colliding, extremely hard to compute, because now there's billions of planets and stars all together merging with each other in some complex gravitational system. It takes hundreds of millions of years for this collision to unfold. In fact, our own galaxy right now is in the middle of an ancient collision that's still happening today. How many knew that? We're in the middle of colliding with other galaxies right now. It's been happening for hundreds of millions of years, so don't panic. It's okay. And these galaxies can collide with no two stars touching each other, because stars are so far apart, many light years apart on average, that two galaxies can collide, pass through each other, and no two stars will collide, or no two planets will collide, because they're so sparse. But they'll completely misshapen each other gravitationally and maybe even merge into a single galaxy. That's okay. Very hard to predict that. For all the same reasons, it's hard to predict weather and other phenomena like that, and tsunamis and earthquakes. It's basically high sensitivity to initial conditions and a lot of chaos rearing its ugly head, and of course undecidability on top of that. So protein folding is not impossible, it's just difficult, because you can look at all combinations of how a protein can fold onto itself, and how it folds onto itself can determine disease and drugs and cures for diseases and ailments. And so we'd love to be able to solve the problem of protein folding. That one is almost doable. We're kind of on the verge of being able to do that. It's NP-complete technically, so computationally it's intractable, but there's all sorts of heuristics that we can use. Other chaotic systems involve lightning, and it's diffusion processes, fluid mechanics in general. It's hard, to solve, predict, to simulate, right? It depends on temperature and diffusion through liquids of other liquids and densities, and of course you get chaos and undecidability very quickly. And fluid dynamics gets even worse when you have turbulence. So a turbulence, you can get a very small scale turbulence. Whenever you put cream in your coffee, that's turbulence right there. And you can actually see the turbulence of the cream in the coffee. Very hard to predict the way the swirls will unfold. Undecidable, in fact. And of course, you get large-scale turbulence. If you have laminar flow of just one dimension or two dimensions, that's easy to do. But if you have three-dimensional turbulence, or even two-dimensional turbulence, eddies coming off of something, that water rushing through it, or even air buffeting, that kind of thing gets very, very unpredictable, very computationally intractable, not simulatable very easily. And even when a drop will form on a faucet, it's the same kind of phenomena. There's turbulence there, chaos. And you have very, very big turbulent systems like, there's Jupiter, and there's a big red spot on it. It's basically a hurricane that's been ongoing for millions of years, the same hurricane. And it's many times the size of our planet. Very hard to predict the structure of this, which way it will go, how fast it'll come across, what kind of swirls there'll be in it, or whether it'll just stop or not. Again, because of chaos, insufficient data, and even if we had no chaos and sufficient data, it'll still be undecidable in general whether such a thing takes any kind of particular trajectory or behavior one way or another. Okay. Now, don't get me wrong, there's very precise Navier-Stokes equations for fluid mechanics, right? And that's exactly the equations right here. They're in differential form, and they completely describe how fluids behave, incompressible fluids. So why can't we just use this equation, implement it, and then we'll have a good simulation of what these phenomena look like, weather and tsunamis and earthquakes and turbulence. And well, there's reality versus theory kind of issues. So there's the Navier-Stokes equation. How many have heard of the Navier-Stokes equation? Okay, so you've heard of them. They're a complete description of what fluids do and don't do. But it's easy to simulate them and use them to predict very simple systems like a two-dimensional wave, standing wave. They'll give you exactly what would happen. Or even a two-dimensional simple wave, like pebble dropped in a pond. It'll show you the waveform and so on pretty straightforwardly. But try to predict, a surfer's wave on the beach from these equations. It looks nothing like that. And in fact, we have no simulations yet that can predict these kind of waves from these equations, even though these waves are implicit in these equations. Theoretically, you should look at this equation and say, oh yeah, it's a beautiful wave with a crest, breaking over this surfer dude that's trying to surf here. Look how small the human is, by the way. These are big waves. So that's one description of them. Here's another description of them. We don't know how to bridge this gap, even though we know that the complete description of these waves is embedded implicitly in these equations. So it's kind of almost frustrating or tantalizing that this is the case, yet we don't see visually and viscerally the beauty of these waves in this equation, even though we know it's there. So we're slowly trying to bridge that gap. And now when people make movies, James Cameron, when he makes Avatar and very sophisticated animated movies, they're using equations like this to actually show the scenes, whether it's fluids and waves breaking and birds flying, aerodynamics and weather systems and clouds, and they're doing it. They're using physics simulations to actually produce these films. So it's pretty cool. And by the way, the Navier-Stokes equation has got $1 million prize on it from the Clay Institute. That's one of the 7 problems at the $1 million problem per problem prize the Clay Mathematics Institute, the Millennium Prize, was put on. Right? So there's a Navier-Stokes equation, and one of them was actually solved, the Poincaré conjecture. Remember Perlman in 2006 solved the topological problem of Poincaré, won $1 million prize, didn't want to collect it, actually. Once the field medal, said no thank you to that too, interestingly. Now there's 6 problems. One of them is p equal to NP. We'll talk about that, NP-completeness, in a couple of lectures soon enough. But there's a Navier-Stokes equation. It's one of those things. And of course, it all goes back to Hilbert, right? We talked about Hilbert at great length. Here's probably the simplest chaotic system that I've ever seen or even exists. So you all know what a pendulum is, right? It just rocks back and forth with regular periodic motion and very simple equations. And assuming no friction, it just goes on forever with a certain period and no big deal. Now, take a double pendulum. Connect the pendulum to the end of another pendulum. Chaos. Immediately, you got mechanical chaos. True chaos, not just the word, but mathematical definition of chaos. So to tell whether that green pendulum will ever go over the top, completely loop-the-loop over the top, undecidable, turns out. And a triple pendulum, forget about it. And of course, you can compound them all you want. But even a double pendulum, and the equations are pretty well known, but simulating them is extremely sensitive to initial conditions. And here's a graphic of showing you the movement of the end of the second pendulum, and it looks chaotic too. Right now we're tracking the end, not just visually like that, where instantaneously it is, but where it's been over time. And whether it goes completely over the top, we have no algorithm to determine that, even though it's only 2 degrees of freedom. And it's in the plane, so it's 2-dimensional. And it's pretty straightforward and completely well-defined. There's no ambiguity about the definition of these things. You know, there's gravity pointing down. There's 2 pendulums. That's it. There's not a whole lot more going on here. But very quickly you get chaos. So very, very simple system. Once I visited Caltech, and they had a physical embodiment of this thing. 2 metal pendulum, very, very heavy. And you'd align them, and they're all on the same axes. And you'd align them in the 2 double pendulums and try to push them forward with the same speed, with the same momentum, and see what happens. And the first few seconds, they will all be doing the same thing like this, and all of a sudden they'll start diverging, and then one will have nothing to do with each other. And try as though you may inject the exact same speed and the same velocity and the same momentum into both. You get very quickly a visceral demonstration of this phenomena of chaos, even in this simple system. And of course, you got fractals out of chaos, and this is a very ordered version of chaos, right? So you have fractions in any dimension. In fact, fractals can take fractional dimensions. You can have fractals that have dimension 1.7, or something like that. So dimension no longer is an integer. How many knew that? A dimension doesn't have to be an integer, like 1 dimension. It could be a fractional number. Now you know. You can read about it. Several books on the website for this class, like the fractal geometry of nature and a few others. And fractals occur in nature all the time. This is like broccoli and flowers and trees, and they have fractional geometry and fractional dimension. And these are examples from real life. And there's lots of other examples like lightning and crystal growth and snowflakes. These are all fractals, objects with fractional dimension. And even coastlines on the macroscopic level, rivers and river deltas, these are also fractals. And fractals have lots of applications in computer graphics and simulations and market analysis of stocks and bonds and financial markets. And in Harry Potter, when you had like lightnings coming out of magic wands and so on, they were modeled using fractals, now you know. And in the human body, there's fractals in terms of the pulmonary system, arteries, and the lung structure, and so on. Very, very interesting set of concepts. So we're running out of time, but we'll keep talking about that next time, computational universality. Solve lots of problems, and we'll see you next time.